In this video, you're going to learn about Newton's laws and its application. First law of Newton states, an object subject to no external forces is at rest or moves with a constant velocity if viewed from an inertial reference frame. Hence, your first law of Newton, summation of forces is equal to 0. For your second law, for any object, the summation of forces is equal to mass times acceleration. For your third law, forces occur in action-reaction pairs F A B is equal to negative F B A, where F A B is the force acting on object A due to its interaction with object B, and vice versa for negative F B A. Gravity. Here is an example on how to calculate gravity. What is the force of gravity exerted by the Earth on a typical physics student? Okay, we have the following parameters. The mass of the student is equal to 55 kilograms. The Earth's gravitational constant is equal to 9.81 meters per second squared. To calculate now the force of gravity, it is equal to the weight of the student, which is calculated as the mass of the student times the gravitational constant of the Earth, giving us 55 kilograms multiplied with 9.81 meters per second squared, gives us 540 newtons as the force of gravity or the weight of the student. As you can see on the right side, we have the free body diagram of the student. The mass of the student is pointing downwards, or her weight is pushing downwards. Okay, so FSE is equal to FG is equal to mass times gravity. Okay, we have the following: mass versus weight. An astronaut on Earth kicks a bowling ball and hurts his foot. A year later, the same astronaut kicks a bowling ball on the moon with the same force. His foot hurts A more, B less, C the same. So what is your answer? The masses of both the bowling ball and the astronaut remain the same, so his foot will feel the same resistance and hurt the same as before. Okay. However, the weights of the bowling ball and the astronauts are less. Why? Because weight is equal to mass times the gravitational acceleration of moon, whereas your gravitational acceleration on moon is weaker than the gravitational acceleration on Earth. Thus, it would be easier for the astronaut to pick up the bowling ball on the moon than on the Earth. We have your second law of Newton's motion. So your second law says your summation of forces is equal to mass times acceleration. Key phrase here is for an object. So before we can apply F is equal to ma to any given object, we isolate the forces acting on this object. Consider the following case. What are the forces acting on the plank? P is equal to plank. F now is represented as the floor. Your W is represented as your wall, and E is represented as your earth or the ground. So you can see in this free body diagram of the pack, okay, of the plank, we have your forces acting on the plank as it is leaned on the side FP, W, and FWP. Okay. Now, FPE force points downwards and FEP points upwards. Your FPF points upwards and your FFP points downwards. Now, if we're going to isolate the plank, okay, we're just going to consider the following forces. We have your FPF, FPW, and FPE. In this example, the blank is not moving. It is certainly not accelerating. So F net is equal to mass times acceleration. Since it's not accelerating, your acceleration is equal to 0. So F net is equal to 0. Okay. To consider now the summation of forces, FPW plus FPF plus FPE is equal to 0. This is the basic idea behind statics, which we will discuss in a few weeks. An example of dynamics problem. Here, a box of mass m is equal to 2 kilograms slides on a horizontal frictionless floor. A force F of x is equal to 10 newtons. Pushes on it in the x direction. What is the acceleration of the box? Okay, as you can see on the free body diagram, we have the box, okay? Then a force F is equal to Fx pushing a mass m of the box as 2 kilograms. And then as it moves, it has an unknown acceleration. If we're going to analyze the free body diagram of the figure, okay, we're going to consider forces acting on it. So we have the F force where it pushes the box. Then we have your FBF as your normal force, FFB as your weight. Okay. Then we have your FBE as your weight of that box and FEB as the normal force acting on that box. Okay. Draw a picture showing all the forces and isolate the force acting on the block. Okay. After drawing the free body diagram of the block, solve for the Newton's equations for each component. Okay. The summation of forces x is equal to mass times the acceleration at the x-axis. And then if we're going to consider the y component of the forces, we have FBF minus mg is equal to mass times your acceleration at y component. Why is it your mg, or the weight of the box, is minus? Because it's pointing downwards. And then we have your FBF, which points upwards. So that is positive for FBF and negative for the weight of the box, or mg. If we're going to further simplify the solution, your force at x is equal to mass times acceleration at x. So getting your AX, we have to divide your force of x with the mass, okay? So in this example, we have your 10 newtons divided by 2 kilograms. So the acceleration of the box is 5 meters per second squared. If we're going to get now your force BF, we're going to consider the y component of forces. FBF minus mg is equal to mass times acceleration at y component. But since the force that influences the acceleration of the box is horizontal, or in x component only, your acceleration y, or vertical acceleration y, ay, is equal to 0. Hence, FBF is equal to mass times your gravity. The vertical component of the force of the floor on the object, FBF, is often called as the normal force. It is stated earlier. Since AY is equal to 0, your normal force is equal to mass times gravity in this case. Okay? So we have the recap. Your f of x pushes the box. And then we have your normal force, which is pointing out upwards. N is equal to mass times gravity. And then we have the weight of the box pointing downwards as mass times gravity. Your AX is equal to f of x all over m. A block of mass m rests on the floor of an elevator that is accelerating upwards. What is the relationship between the force due to gravity and the normal force on the block? Is it A, normal force is greater than the weight? B, normal force is equal to weight? Or C, your normal force is lesser than the weight? Let's reveal the answer. All forces are acting in the y direction, so use F total is equal to mass times acceleration. N minus mg is equal to ma. N is equal to ma plus mg, thus increasing the amount of your normal force. Therefore, your normal force is greater than the weight or mass times gravity. Tools, we have the ropes and strings. Can be used to pull from a distance. Tension T at a certain position in a rope is the magnitude of the force acting across a cross-section of the rope at that position. The force you would feel if you cut the rope and grabbed the ends. An action-reaction pair happens. Okay? As you can see on the figure, we have the tension. Okay? Tension that is applied on the ropes. Okay? Consider a horizontal segment of the rope having mass m. If we're going to draw a free body diagram of this, we're going to ignore the gravity. Okay? As you can see here, okay, we have your m, mass of the rope, that is being stretched. So we have your tension or first tension or both tensions pulling outwards or stretching out the strings, okay? But the movement of the stronger force is to the right, okay, on the side of tension 2. Using Newton's second law in the x direction, F net now is equal to positive T2 because it's to the right minus T1 minus T1 because it is to the left. You're going to equate it now to the mass times acceleration, okay? Mass of the rope times the acceleration of the force applied to the rope. So if m is equal to 0, then or the mass of the rope is negligible or super light, then your first tension is equal to second tension. An ideal massless rope has a constant tension along the rope. Okay? If a rope has mass, the tension can vary along the rope. For example, a heavy rope hanging from the ceiling. We will deal mostly with ideal massless ropes. The direction of the force provided by a rope is along the direction of the rope. Okay, we have your block here with mass mg or weight is equal to mg. Okay, your tension now is acting opposite on the weight of the block. Okay, that is to balance the forces. Since ay is equal to 0, the box is not moving. Okay, it's in a stationary mode. Your tension now is equal to the weight of the box or mass times gravity. Mass of the box times the gravity. A fish is being yanked upward out of the water using a fishing line that breaks when the tension reaches 180 newtons. The string snaps when the acceleration of the fish is observed to be is 12.2 meters per second squared. What is the mass of the fish? Is A, 14.8 kilograms, B, 18.4 kilograms, C, 8.2 kilograms? Let's reveal the solution. The first thing you're going to do is to draw the free body diagram, okay? So we are not given with the mass of the fish. So we have the tension which is pointing upwards, and then the weight or the mass of the fish that is downwards. The acceleration now, since this is pulled upwards, we have 12.2 meters per second squared. If we're going to balance now the forces, your force net is equal to mass times acceleration tension or positive tension minus the weight of the fish, as mass times gravity is equal to mass of the fish times the acceleration. Now, if we're going to further simplify this, tension now is equal to mass times acceleration plus mass times gravity. Okay? Solving now for the mass gives us tension all over gravity plus acceleration. Plugging in the values, we have 180 newtons all over 9.8 plus 12.2 meters per second squared gives us the mass of the fish as 8.2 kilograms. So the fish is light. Another type of problems, we have your pegs and pulleys used to change the direction of forces. An ideal massless pulley or ideal smooth peg will change the direction of an applied force without altering the magnitude. Okay? Please take note of the diagram. We have your first force, okay? Which is dragging the whole system to the left, okay? And then pushing your second force upwards. Note that F1 is equal to F2, but both forces is in absolute values. An ideal massless pulley or ideal smooth peg will change the direction of an applied force without altering the magnitude. So we have your FWS is equal to mg, which is to the right. Okay? And then we have this one, the tension that is upwards, which is supporting to the mass of the block. If we're going to isolate and then consider the free body diagram of the block, tension now gives us mass times gravity, or your tension is equal to the weight of the block. Okay? Hooke's law. The force exerted by a spring is proportional to the distance of the spring is stretched or compressed from its relaxed position. F of x is equal to negative kx, where x is the displacement from the relaxed position and k is the spring constant. Yeah, as you can see on the diagram, we have the relaxed position of the spring and then the contracted position of the spring as f of x is equal to negative kx, which is greater than 0. Okay? Where x must be what? Lesser than 0. Why? Because it contracted. Your displacement is negative, so it must be lesser than 0. Then if you are going to expand the spring, the displacement increases, so your x is greater than 0, giving us your f of x is equal to negative kx, which is what? Lesser than 0. Springs can be calibrated as well as the applied force. We can calibrate scales to read newtons. Our fishing scales usually read in weights in kilograms or pounds. 1 pound is equal to 4.45 newtons. Take note here, the pound is in pound force. Okay? A block weighing 4 pounds is hung from a rope attached to a scale. The scale is then attached to a wall and reads 4 pounds. What will be the scale read when it is instead attached to another block weighing 4 pounds? Is it A, 0 pounds, B, 4 pounds, C, 8 pounds? Draw the free body diagram of one of the blocks, okay? If we're going to isolate one of the blocks, your tension now is pulling outwards, and then your weight is downwards. So tension now is equal to mass times gravity. Now, considering the total force summation to 0, why is it 0? Because the whole block is in stationary mode, okay? Your tension now is equal to mass times gravity, or the weight of the block, which is equal to 4 pounds, okay? The scale reads the tension in the rope, which T is equal to 4 pounds in both cases, okay? Another problem is this accelerometer A weight of the mass m is hung from the ceiling of a car with a massless string. The car travels on a horizontal road and has an acceleration a in x direction. The string makes an angle theta with respect to the vertical y-axis. Solve for theta in terms of acceleration and the gravity. Okay? If we're going to draw the free body diagram of the accelerometer, okay, we have the mass of that as m, okay, the weight now with the gravitational force mg, and then the tension in angle theta. Okay, if we're going to consider further the components of the free body diagram forces of the accelerometer on this problem, your f of x is equal to tension at x is equal to t times sine of theta is equal to mass times acceleration, and then the y component, Fy is equal to Ty minus mg. Okay? How are we going to get the y component of your Ty? To further expound it, you're going to use the trigonometric identity. So we are given with your T tension. And then to determine now the trigonometric equivalent of your Ty, okay? So we are given with hypotenuse as T, and then adjacent of your Ty, okay? Adjacent and hypotenuse, that is or cosine, okay? So T cosine theta minus mg is equal to 0. If we further simplify and eliminate T, gives us your tangent of theta is equal to acceleration all over the gravity, okay? Alternative solution using vectors, but it is not systematic, okay? Now the following, your T, that is your hypotenuse, which is pointing to your north of west, okay? And then your weight of the accelerometer as downwards, mg, and then your F net as to your left, okay? If we're going to consider the following and then use trigonometry, but remember your F total is equal to summation of forces, or F net, which is equal to the mass of accelerometer times the acceleration, okay, which gives us tangent of theta is equal to AG. Say the car goes from 0 to 60 miles per hour in 10 seconds. 60 miles per hour in meters per second gives us 27 meters per second. And then the acceleration delta V all over delta T is equal to 2.7 meters per second squared. So your acceleration all over the gravity is 2.7 all over 9.8 would be equal to 0.28. So the tangent that is subtended by the accelerometer gives us 15.6 degrees. A block of mass m slides down a frictionless ramp that makes angle theta with respect to the horizontal. What is the acceleration A? Define the convenient axis parallel and perpendicular to the plane. Acceleration A is in the x direction only. So if we're going to consider the x and y component of the forces, mg sine theta is equal to mass times acceleration, or your A now is equal to gravity times sine of theta. And then your normal force minus the weight cosine of theta is equal to 0. Hence, your normal force here is equal to weight cosine of theta. Okay. Alternative solution again by using vectors. Your A now here is equal to gravity times sine of your theta. And then we have your normal force. It is equal to the weight, or mg, multiplied with the cosine of theta. The triangles are similar, so as you can see here, the given triangle of the inclined plane would be equal to the angle here on this conformation. Remember, on this conformation, the angle here is equal to the angle of the inclined plane with respect to the horizontal. Remember, this is in application of similar triangles. A black mass is equal to 5.1 kilograms is supported on a frictionless ramp by a spring having constant K is equal to 125 newtons per meter. When the ramp is horizontal, the equilibrium position of the mass is at x is equal to 0. When the angle of the ramp is changed to 30 degrees, what is the new equilibrium position of the black x1? Is it A, x1 is equal to 20 centimeters, B, 25 centimeters, C, 30 centimeters? Okay, so on your lower left side of your screen, you can see here the horizontal conformation of the block with the spring. And then on the right side, we have the inclined conformation of the block with the spring at 30 degrees. Now, the first step to solve this one is we're going to consider the force body diagram. Okay, your theta here is equal to the angle here, okay, and here. Remember that the weight points downwards, so m times g, okay. The friction acted on the block Fxg is equal to mg sine theta, and then the force which is stretching the spring in the block is pointing to your north of east, whereas your force here, F of xs is equal to negative k. Multiply it with the x1 as your displacement. Mg sine theta minus kx1 is equal to 0. This is for the summation of forces with respect to this inclination. Whereas we're going to simplify to get the displacement x1, okay, simplifying these terms gives us your mass times gravity sine of theta all over the spring constant k. Plugging in the values, we have your 5.1 kilograms, multiply it with Earth's gravitational acceleration times 0.5. Sine of 30 degrees is actually 0.5 all over the spring constant at 125 newtons per meter. Hence, solving your displacement gives us 0.2 meters. Okay? Two blocks of masses M1 and M2 are placed in contact on a horizontal frictionless surface. If a force of magnitude F is applied to the blocks of mass M1, what is the force on the block of mass M2? Okay? So we have the following diagram. Your force is applied on the larger block M1. So on this problem, what is the force on the block of mass M2? So we're going to determine the force applied on your second block. Now, if we're going to realize your total force is equal to the summation of both masses of the block, so M1 plus M2 quantity, multiply it with your acceleration. To determine now your acceleration, divide both sides of equation with M1 plus M2 gives us your force all over M1 plus M2. Now, if we're going to draw the free body diagram, F net is equal to MA. F force applied to your first block and second block would be equal to your M2 multiply it with your acceleration. Now, if we're going to substitute the value of your A here from what we get from the first equation, your F21 is equal to M2, multiply it with your force all over mass 1 plus mass 2. Hence, simplifying this one, your F21 is equal to M2, multiply it with your F all over summation of masses 1 and 2. A box is suspended from the ceiling by two ropes, making an angle theta with the horizontal. What is the tension in each rope? To determine now this type of problems, okay? First, we have to illustrate the statement of the problem. Now, the block is supported with two ropes. As you can see here, we have your tension. Since we're going to assign both angles here as your theta because it is stated on the problem. We're going to assume that it is not stated on the problem that they are in different angles. Okay? If we're going to determine the x component of the forces, we're going to consider the x component of the first tension and then the second component, second x component of the second tension, okay? So T1 cosine theta minus T2 cosine theta gives us 0. And then the horizontal component, we have your T1 sine theta plus T2 sine theta minus the weight of the block as mg. Gives us your T1 is equal to T2 mg all over 2 sine of theta. Okay? Then a boy ties a rock of mass m to the end of the string and twirls it in the vertical plane. The distance from his hand to the rock is r. The speed of the rock at the top of the trajectory is v. What is the tension T in the string at the top of the rock's trajectory? Draw a free body diagram for this type of problem, okay? Now, the trajectory of the rock, we have your tension pulling downwards and then the weight of the rock pulling downwards as well. So your F net is equal to weight of the um, oh, plus the tension. So F net is equal to mg plus t. We have your acceleration in y direction. Ma now is mv squared all over the r. And then force is equal to mass times acceleration. Simplifying both terms, mg plus t is equal to mv squared all over r. Further, getting your tension here, t is equal to mv squared all over r quantity minus your weight. What is the minimum speed of the mass at the top of the trajectory? So determining the speed here, further simplifying the equation earlier, gives us your v is equal to the square root of your radius times your gravity. A skier of mass m goes over a mogul having a radius of curvature r. How fast can she go without leaving the ground? Okay. Is it A? V is equal to m r g, okay, raised to 1/2. V is equal to the square root of r all over g all over m. V is equal to quantity r of g raised to 1/2 or the square root of r multiplied by g. So the answer here is derived earlier as v is equal to the square root of r multiply it with g. Okay, so the recap of today's lecture, we have the following: the free body diagram, the tools we have for making and solving problems for your ropes and pulleys, and Hooke's law. Okay, we have the following: your accelerometer, inclined plane, and motion in a circle. So that concludes my presentation for now. God bless my students.